Okay. I think that we are streaming more or less in a few minutes, few seconds. I hope. So, I think that we are streaming more or less in a few minutes, few seconds. I hope. Yes, do you hear me now? It's good. My sound, it's good.
Yes, yes.
Okay. So welcome everyone to our, I think that we are great women, more or less in a few minknow few seconds. I hope.
Look, I think
yes,
you should turn
yes,
on
I
now.
know. It's good. I know. All right. Sorry. Okay, I would like to speak some words to begin our meeting. Celebrate Women in Mathematics is an event based on the May 12 initiative to celebrate the women in mathematics. I think that it is a good thing we would think about the representativeness on in STEM, and I'm very glad because we could to make it 3 years, 4 years, 3 years. We started in 2019 with a little meeting in Federal University of Rio de Janeiro. Then in 2020, we would like to make a presential meeting, a greater, larger meeting, but the pandemic take of us. And in 2021, we have made our meeting online, and it was a very great meeting. And I hope that this one is going to be a very great meeting too. And all people, all gender, whatever, are welcome to hear, because this is not only a meeting to women in mathematics. This is our flag, but this is also a meeting to everyone in everywhere. Okay, so I would like to thank you all to come here and to give us your support. I'm going to put our video, and then I pass the word to Jacqueline. Okay. Hope you're here. Are you here?
No.
Why not?
Now it's black. I don't know what happened. It's moving, but don't hear.
Eu quero demonstrar que gosto imensamente de você por uma fração infinitesimal.
Oh, we can't hear you. You're muted, Luciana.
Yeah. Yeah, you're still mute.
I'm mute because you are hearing two times, but
Okay.
I'm going to choose to fix it. Sorry.
Pra que dividir sem raciocinar? Na vida é sempre bom multiplicar. E por A mais B eu quero demonstrar que gosto imensamente de você. Por uma fração infinitesimal, você criou um caso de cálculo integral. E para resolver este problema, eu tenho um teorema banal. Quando dois meios se encontram, desaparece a fração. E se achamos a unidade, está resolvida a questão. Para finalizar, vamos recordar que menos por menos dá mais amor. Se vão as paralelas ao infinito se encontrar, por que demoram tantos corações a se integrar? É que infinitamente, incomensuravelmente, eu estou perdidamente apaixonada por você. Pra que dividir?
I think this time it is working.
Yeah, it did. It was good.
Okay.
Well, it's quite powerful to see all these women face and together and with a nice music. I don't know, I cannot hear, Luciana.
Don't you
Yes.
hear me? Okay.
Now, yes. Yes, yes.
The music is from Tom Jobim.
Pronto, gente, a gente trocar ao vivo, tá? Tá bom.
Oh my God. Okay. So I pass the word to Jacqueline. Thank you all. Enjoy it.
Thank you, Luciana. So, well, I should really thank her, not just to pass the word, but to have been, I played made the joke in the beginning that Luciana is the boss. She for sure, she put her blood and sweat. Yesterday was the Mother's Day. She's a mother, and she was the whole day texting everyone and putting everyone to work. So I'm very glad that she's my colleague and also my friend, but give me a lot of pride to be working with her, because she has this really energy, and this is good. You feel guilty if you don't work hard as her. So I hope we have a very nice week. So and pays back all the work that we have done. So thanks for the group of students also that have worked a lot, that is and supporting us, and all people that are related to the work, the scientific committee, all the speakers, and then So I hope we will have a nice week. So for starting our week, I have a great pleasure to introduce Gemma Huguet. She's a professor at the Universitat, I don't know if I'm going to pronounce correctly, Universitat Politécnica de Catalunya in Barcelona. She works in a very exciting field. She works in dynamical systems with some applications in neuroscience. I have had the pleasure to attend some mini course that she gave online at our university, the Federal University of Rio. It was great. And she has kindly accepted to talk in this conference this week for us. And I hope you all enjoy her talk. Thanks, Gemma, please.
Thank you very much, Jacqueline, for the nice presentation. And thank you all for putting together this very interesting and nice conference to celebrate women in math. So congratulations to all of you, and thanks for the invitation. I'm really happy to speak here. So as Jacqueline, when she presented me, she already mentioned that I'm working on applications or like providing quantitative and mathematical tools to neuroscience in order to provide answers to questions that arise in this field. So let me start with this preface that basically to justify my work is that neuroscientists need quantitative tools to face classical problems, but also new problems that appear with the new technological advances. And thanks to models and simulations, scientists from several disciplines and physicists, engineers, but in particular mathematicians have approached the neuroscience field in a very interdisciplinary work. So the goal for today's talk is to provide you a taste of the role that mathematics can play in the research of neuroscience. To start, let me bring you to the field of neuroscience and say that the object of study for this field is the brain. And the brain is a very complex organ because it consists of 10 to the power 12 neurons, which are the basic unit cell that performs computations. And each cell might make connections with an average of 1,000 other cells. These connections called synapses, they increase the complexity of the system because they add up to 10 to the power 15. So since this is a very complex structure, the strategy to approach it is to attack or like to tackle the questions related to this organ, but at different spatial scales. So one can look at the whole organ, and possibly this is what psychologists do, and try to understand how we use the whole organ as a whole to perform tasks. But then we can look also inside this organ and focus on a particular region, for instance, the visual cortex, which is this part of the brain that encodes information coming from the eyes. Or we can even look deeper inside and then look at the scale of circuits. This consists of structures of about like hundreds of thousands of neurons connected to each other in a particular way, and see what is the dynamics that emerges out of this circuit. We can even look farther inside, go to the level of a single neuron, or even inside at the molecules and structures of the neuron. So I will mainly focus at the level of circuits because this has been hypothesized as the basic unit, or like the smallest unit whose dynamics or whose behavior is whose dynamical properties are correlated with subject's behavior. Let me say that the math tools to provide answers or to help understand how the brain works are very wide, and they range from statistics, data analysis, information theory, to, since we are talking about neurons and connections, so this can be seen as graphs, and then the structure of the network also plays a role. So topology is also another part of math that has useful applications to this field. And the other part is that since these are structures that they have dynamics and that they interact with each other in a dynamical way, so tools from differential equations, so continuous models involving differential equations, ordinary differential equations and partial differential equations and stochastic differential equations. So all the techniques coming from these fields are useful for the neuroscience, for neuroscience. So for this talk, and since this is my background and my expertise, I'm going to focus on tools from dynamical systems. And what we're gonna do is like I'm gonna try to present you a problem or a question that emerges in neuroscience. But first, let me say that, as I said, the basic unit is the neuron, and from the neuron, the experimentalist can record the voltage. That's the variable of interest, and is the variable that we want to model and describe the evolution, because the voltage of a neuron typically shows this type of pattern of activity. So there are moments, so that's the voltage, this is time on the x-axis. Sometimes this neuron is at a resting state, so the voltage just fluctuates around value. But then suddenly we see these spikes or these rapid changes in the voltage that are known as action potentials. And when we see a neuron that is showing this type of spikes or action potential repeatedly, we say that this neuron is active. There are classical models in dynamical systems to describe the evolution of the voltage of a neuron. The most classical one is the Hodgkin-Huxley. But the one that I'm going to need for today's talk is a very simplified model that is called the integrate and fire model, that basically describes by means of this linear differential equation, as you can see, the voltage of a neuron, but it has the particularity that these action potentials or these spikes describing activation of a neuron are just described in this model by means of a reset condition. That is, the voltage is the evolution of the voltage is described by this equation, but then when this voltage reaches a certain threshold, okay, the voltage is reset back to the resting state, and we say that a spike has occurred. This is a type of model that is very simple and is very useful when we only want to describe when the neuron is showing or is having a spike, is having activity. We're only interested in the timing of this. So when we put this neuron in a network, this starts to interact with nearby neurons in two possible ways. One is that if this neuron is excitatory, it means that when this neuron has activates, then it tends to promote that the neurons to which it is connected, they're going to activate as well. However, if this neuron is inhibitory, what it will do is it will try to prevent that the neurons to which it is connected, that they have activity. So these are like two opposite effects. So when we put a neuron in this network, we want to describe the activity of the overall network of cells. And what we have is that for each individual neuron in the network, we're going to have the evolution of the voltage of this neuron, which is shown in this voltage trace. But as I said, from the voltage evolution, we only care about the instance of time at which this neuron is giving a spike or is showing these action potentials, which are represented by these vertical bars along this timeline. So when we have like a network consisting of hundreds of thousands of neurons, like a large group of neurons, we are gonna extract from each neuron in the network this type of information in the time axis, like the times at which each neuron gives a spike. And we were gonna provide this information in what is called a raster plot. So on the x-axis, we have time, and on the y-axis, we have the index of each neuron. And for each neuron, we put a dot at the times when this neuron is giving a spike. from these raster plots is easy to, are very useful because one can visually observe like if there are some sort of overall pattern in the network. For instance, in this example here, what we see is that there is initially there is a moment in which it seems that all the neurons in the network show high firing rate, and then there is some period of time, or like some period of time in which the activity of the network decreases. And this can be observed if we take the average activity of the network. That is, we take a small time being and we compute like how many spikes we have in that time being, and then we can compute the spikes per second in the network. And as we visually observed in the raster plot, we can confirm this in this average in this plot of the average activity of the network, showing the average activity, okay? That we observe this oscillatory pattern, that is moment in which that seems that a large amount of cells in the network have spikes, are active, and then moments in which the overall activity of the network decays. So the number of spikes in the network decreases. And this shows this oscillatory pattern. Well, this is what I would like to focus on this talk, is to talk about neural oscillations, okay, and rhythms. So when one takes registers or like of activity in the brain, the presence of oscillatory activity is very widely spread in the brain. That is, and at very different organizational levels. So we observe oscillatory behavior at the level of single neurons. Just the activity of a single neuron might show rhythmic activity, and also at the level of the network that I just discussed, like when we take the overall activity of a group of neurons in a network. And when we register this activity via, for instance, encephalograms, we observe that there appear oscillations at very different frequencies, ranging from a few hertz to hundreds of hertz. But there is a particular range of frequencies that ranges between 30 and 100 hertz that is called this gamma band range. In the field is known as the gamma band range, in which it is when one takes registers of the electrical activity, it's very common that we observe oscillations in this range. And this is observed across different species, across different brain regions, across different recordings of subjects performing different types. It is very common that one registers oscillations at this gamma band range. And then one of the questions that emerges is like, what is the role of these oscillations? So we have that many works that oscillate, that associate oscillations to specific tasks, but their functional role is not completely understood. It's like why it is so common that we observe oscillatory behavior in the brain. What is the functional role of these oscillations? Do they have a role, or it's just a mere consequence of the type of interactions between neurons? And one of the theories that try to provide an explanation or a role for this oscillation is this theory known as communication through coherence, proposed by Pascal Fries in 2005 and revisited in 2015. And he proposes the following, is that these oscillations in the brain might emerge via the interaction of excitatory and inhibitory populations. That is, when we have a population that is excitatory and activates, so its activity raises, this activates an inhibitory population, okay, that at its turn sends back inhibition to this population, producing that the activity of this population goes down. Then the effect of these inhibitory cells is felt for a while, and once the effect is washed out, these excitatory cells may activate again, repeating this pattern periodically. So via this interaction of excitation and inhibition, one can generate oscillations, and these oscillations reflect different excitability properties along a cycle. What does it mean? Is that if we consider this a network of excitatory cells, and now this network receives an input while inhibition is acting, probably this input won't have any effect, because the inhibition will prevent this input to have an effect onto the receiving population. However, if the external input arrives at this phase of the cycle, that is when the inhibition has been washed out, the receiving population is going to be more receptive to this input and probably is going to respond to this input. That means that this external input will affect the activity of the target network. So the theory proposes that these oscillations regulate the information flow. That is, the oscillations is like if this is someone who is listening, but in a rhythmic way. So sometimes you cover your ears and then you uncover your ears in a periodic way. This means that if the input arrives, or the sound arrives when my ears are covered, I'm not gonna receive the information. However, if the sound arrives when my ears are uncovered, then I will receive the information. So some sort of these oscillations play this role, okay? And also, what I need is that if I want to produce like a good communication, so communication must be established, the person that speaks, if it speaks periodically in a way that is correctly phase locked so that the sound arrives when my ears are uncovered, then communication is going to be established. So based on this hypothesis, they have proposed a mechanism where oscillations play a role in the task of selective attention. Selective attention is when, for instance, this is an example of selective attention. So in the visual field, you have several objects, and then someone gives you the instruction to pay attention, in this case, to the apple. So what must happen in the brain is that what is seen through your eyes is all the time the same, but at some point in the brain, there must be something that makes that you only pay attention, or you are only focus on the information coded, so on the information coming from the neurons coding for the apple, and then ignore the others. So these oscillations, or this theory proposes that you can do this with oscillatory behavior. So if the neurons coding for the apple and the neurons coding for the pear, they send the information in a periodic way, okay, and this information is sent to a target network that is oscillating in that sense that is listening or not, okay, in a periodic way. If the periodic inputs are properly phase locked with the target network in such a way that the inputs arrive when this is more receptive, communication with the apple is going to be established. However, if this group of neurons that have also periodic activity and they are sending information to the target group in a periodic manner, but badly phase locked in the sense that when the inputs arrive, this target network is not listening, okay, is not excitable, then these inputs will be ignored. And then this is how you're going to pay attention to one or the other. And it is possible to switch between one or the other by means of phase changes. So in this context, it is using tools from phase dynamics to understand the phase locking patterns that emerge between oscillatory systems, between coupled oscillatory systems, might be useful to model this type of biological hypothesis or biological or questions arising in the field of neuroscience. So let me now jump to the mathematical model and the math tools for this project. So what we're going to consider, like we're going to model the activity or the excitability properties of a target network. Okay, and we're going to consider that our target network consists of a group of excitatory cells and inhibitory cells. The excitatory cells self-excite each other and excite the group of inhibitory cells. And this group of inhibitory cells, they inhibit each other and inhibit the group of excitatory cells. So in each of these neural populations, we're going to put like about thousands of neurons, and each neuron, the activity, the voltage of each neuron is going to be described by what it's called a quadratic integrate and fire model, which is a generalization of the integrate and fire model that I presented before. And moreover, to introduce, we are going to make that the group of neurons to introduce some heterogeneity by modifying a parameter and taking the values of this parameter from a Lorentzian distribution. And then we are going to consider that they might also receive an external constant input, and then the couplings that I just discussed. So we can simulate this network, but as I mentioned, like each population consists of like thousands of neurons. So this means simulating at least one equation for each neuron. So it's a very large system of differential equations. So this, in order to see the output dynamics, we must rely on numerical simulations for this. But recently, a group actually in Barcelona, so this group of scientists, Montbrió, Pazo, and Roxin, in 2015, proposed a mean field model describing the average activity of this network using a mean field model, that is a reduced system of differential equations that describe the mean firing rate of the excitatory population described by the variable Re, and the mean voltage of the excitatory population of the cells or the neurons in the excitatory population. And the same for the inhibitory one. Plus these differential equations here that describe the couplings between them. But the important thing is that in this case, with a reduced model of 8 differential equations, we can simulate exactly the average dynamics of the full spiking network model. Okay, and this gives a great advantage because we can apply dynamical systems tools to this reduced model, and they are more amenable to analysis than the full model with thousands of equations. In particular, we can identify in terms of the input parameters, or like the inputs to this constant inputs to these cells, like the regions where we're going to find oscillation. So where we're going to see that this network is showing oscillatory behavior, and then it's modulating the excitability properties periodically. So this is, for instance, a simulation showing the activity in black. So in this raster plot in black, that's the simulation of the full model, where each dot indicates the spike time of the corresponding neuron indexed by the numbers in the y-axis. And the average activity of the excitatory population in red and the inhibitory population in blue is shown in these upper plots, where in red and blue, so in color, the color curves corresponds to the simulation of the reduced model with just the 8 equations. And they are superposed, and actually this is hard to see because at the bottom that is in black is the average activity of simulating the full model. And you can see the good agreement between the two of them. So this allows us that using the reduced model, we can apply more tools And we can do some analysis of this reduced model that it's going to be very complicated, or one must rely on simulations if you deal with the full model. So basically, this is going to be our setting. So we are going to consider a network of excitatory and inhibitory cells. Okay. So we are going to consider, going back, let me go back here. So we are going to consider our network of excitatory and inhibitory cells connected in this way. And we are going to choose a set of parameters such that this network shows oscillatory behavior. Okay. That is, the system has a periodic orbit, or a limit cycle in this case, an isolated periodic orbit. Then, so if we assume that we have a system of differential equations that has a limit cycle, and we're going to assume that this limit cycle is attracting, okay, it's hyperbolically attracting. We can parameterize the limit cycle by means of the phase variable. Okay, and we are going to name the parameterization gamma. And since this limit cycle, I said that it's hyperbolic attracting, it has a stable invariant manifold that is foliated, okay, by what it's called the isochrones. That is, in this stable invariant manifold, we can also define a phase in the following way. The points, a point Q in this in the stable manifold are going to have the same phase as this base point here if the orbit of the starting at this point in blue approaches the orbit of the point of the base point in red as time goes to infinite. Okay, and all the set of points having the same property are called the isochrone, and they have the same phase. Okay, so then the notion, using this, the notion of the phase is extended in a neighborhood of the limit cycle. Okay, so this is and then once we have this, once we have this concept, we can compute what is called the phase response curve. The phase response curve measures the phase variation due to a given perturbation applied at different phases of the cycle. That is, we have our periodic orbit that lives in our 8-dimensional space, and here are showing the evolution of the 8 variables versus time. So then if I apply an external perturbation, in this case, I'm going to apply it in the direction of the voltage of the excitatory cells at different phases of the cycle. Then I'm going to displace the trajectory away from the oscillator, and I'm going to put it in another isochrone. So I'm going to change the phase. This phase change is going to be recorded in the phase response curve, which is shown here when I apply perturbation. So in red is when I apply perturbations in the direction of the voltage of the excitatory cells. What I see for this particular problem is that the phase shift is mainly positive. So that means that the phase is so when the phase response curve is positive, it means that the phase is advanced. However, when it is negative, it means that the phase is delayed. So as we can see here, for instance, if we apply pulses or perturbation at these phases of the cycle, there are barely no changes in the phase shift. So the phase shift is barely zero. It barely affects the phase. However, if I apply perturbations in these phases of the cycle, the phase is mainly, as you can see here, there is an important phase change, which is positive. So the phase is advanced, okay? And we make this oscillator to go faster because we advance the phase, okay? And when these perturbations are infinitesimal, we can compute what is called the infinitesimal phase response curve, which is basically given by the gradient of the phase function. Okay, and then if we want to see the effects in a particular direction, we multiply by the vector in that direction. Let me only mention here that computing the infinitesimal phase response curve can be done semi-analytically by solving what is called this adjoint equation that involves the derivative of the vector field, the transpose of the derivative of the vector field. Okay, this is only to say that these curves might be computed semi-analytically by solving this system of differential equations, by finding a periodic solution of this system of differential equations. Okay, so why do we need the PRC? Because the PRC provides information about like how it's going to be the phase change of my oscillator when I apply a perturbation. So now consider that I apply a periodic perturbation in a particular direction described by the vector V. Okay, and I'm going to assume that this perturbation is T periodic, capital T. So then I'm going to assume that, okay, if this perturbation is small enough, I'm going to assume that this is not going to be, this is not going to move the trajectory very far away from the oscillator. So I might just consider that this perturbation produces a phase shift, and the evolution of the phase then is described by this differential equation that I wrote here, and that involves the phase response function Z that I mentioned before. Okay, so then we might focus on studying only the phase evolution. Okay, and then since we put a periodic perturbation and we want to see whether the forced oscillation or the forced oscillator can oscillate at the same frequency, can phase lock with the forcing, okay, it makes sense to look at the stroboscopic map. That is, what is going to be the phase of my oscillator at multiples of the forcing period, capital T, okay? And this is just solving the differential equation for the phase and looking at the phase at this instance of time. Then, if we have a fixed point of the stroboscopic map, this corresponds to a one-to-one phase locking. This means that our forced oscillator goes at the same frequency as the forcing frequency, okay? And they are one-to-one phase locked, okay? And also periodic points of this stroboscopic map correspond to other phase lock states. But for the moment, let's just focus on the one-to-one phase locking. Okay. In order to compute these phase lock states, we can look at the rotation number. Okay. Then, so if we go back, to our system, we had this excitatory, network of excitatory and inhibitory cells that was oscillating, okay? And now we're gonna put an external input that is periodic. But we're gonna assume that this periodic input, we're gonna put a periodic input described by a von Mises density function, which is sort of a circular normal distribution, because we want to modulate the width of this periodic input, okay? With this parameter kappa, as we increase the parameter kappa, as you can see here, what we do is like we make this periodic input sharper when we increase kappa, okay? This is like if the input arrives, so like the sender is providing information in a periodic way, and this information that is providing is concentrated in some phases of the cycle instead of being spread out. Because then if the receiver is sometimes listening or not listening in a periodic way, it is important you concentrate the information you want to send when the listener is with the ears uncovered. Yeah, it's listening. Then is when you want to concentrate the information and send the information. And then afterwards, you don't need to send information. And then send information and not. Okay. So I need that the input is well phase locked with the target network, with the receiver. And also if the information is provided in a more concentrated way, we are going to see if this has an advantage or not. So the first thing that we do is that with this periodic input and using the math tools that I just described is identify the 1-to-1 phase locking regions. We also identify other regions, the 2-to-1 and 1-to-2, but for the moment, let's focus on the 1-to-2. As a function of what? Of the frequency of the external input. So on the x-axis, we have the frequency relationship between the forcer, which is the period is described by T, and the natural cycle of the excitatory inhibitory network, which is T star. And then we also increase the amplitude, the strength of the input. And then we identify in orange the regions where we're going to encounter 1-to-1 phase locking. That is, the input manages to make the forced oscillator to go at its own rhythm. And what we see is that as we increase how concentrated is the input, that the Arnold tongues enlarge, and actually they are nested one inside the other. So it's when we increase the concentration of the input, the Arnold tongues become larger. Okay. Now, we have identified, so inside of these regions, we are going to have 1-to-1 phase locking, okay? But we still don't know whether this is going to be good one or not for communication, because if the receiver and the input are well phase locked, are phase locked, but in a way that when the input arrives, this is not, the receiver is not listening, this input is going to be ignored. Yeah, so we want to see if they are in the good phase locking for communication or not. So we pick values inside this Arnold tongue correspond to 1-to-1 phase locking. And then, for instance, for a given amplitude, we pick 3 frequencies. We fix the amplitude and we pick 3 frequencies. One that is at the leftmost region of the Arnold tongue, and another one which is at the rightmost region of the, well, rightmost, or like close to the right boundary of the Arnold tongue. So notice that when we pick a frequency close to the left border, it means that the input, the forcing frequency is higher than the natural frequency of the oscillator. However, as we move close to the right boundary, we close to this periods ratio equal to 1, it means that the frequency of the external input is more similar or is close to the natural frequency of the forced system. So what we see is that on the left-hand side or close to the left-hand side, the inputs in green arrives much before in time than the inhibitory cells activate. So this means that they are capable to produce an effect onto the excitatory cells because inhibition is not present there. So it's like the cells are listening because they are excitable. And actually we see here, because the firing rate of the excitatory cells is much larger when we inject the input than what it is without the input. However, as we move to the right, what happens is that now the inputs in green arrive closer, get closer and closer to the activation, the natural activation of the inhibitory cells. And actually, there is missing the next step, which is like when it's very close to the right boundary, the input almost steps onto the inhibition. And then what happens is that the effect onto the excitatory cells is barely noticed. Okay, so it's like if this input is ignored. So it seems that when the frequency of the forcing is close to the natural gamma cycle, to the natural cycle, or the natural activation, is close to the frequency, the natural frequency of the cycle, then the phase locking that emerges is not good for communication and the inputs are ignored. However, if the inputs are sent with a frequency that is higher than the natural cycle, it seems that then it is good for communication. This is one input, but then I explained you at the beginning the situation in which the network receives two different inputs, and then whether the network is capable to respond to one while ignoring the other. Okay, so then we consider this setting in which now we apply, apart from the input that we call primary, that is there and manages to entrain the network at its own frequency, we apply what is called a distractor, which is also a periodic input with the same frequency or different frequency, but phase shifted, okay, with respect to the first one. And then we measure, so if the frequency is not the same as the primary, then we end up with a system that is not periodic, it might not be periodic anymore, the forcing. And then, but we can still do is compute what is called the synchronization index or vector strength. It's like, it's looking at what is the phase at multiples of the period of the primary input. If looking at this phase, and then we can put this phase on the unit circle, and when we encounter the phase always on the same point on the limit cycle, or very concentrated around some phases on the unit circle, we can see that the phase locking with the primary is preserved and the synchronization index is close to 1. However, when we encounter the phases at multiples of the period of the primary distributed along the circle, what we see is that the forcer, the oscillator, is not phase locked with the primary anymore. And basically the effect of the distractor is that it has destroyed the synchronization with the primary and also the communication. Because for the communication, we need both. We need phase locking, because we need that the information is sent is well a phase lock with the excitability properties of the receiver, but we also need that the phase locking is the good one. So when we compute this, what we observe is that for frequencies close to the left boundary of the Arnold tongue, when we apply the distractor, the synchronization index is still very high. The synchronization index with the primary is still very high, very close to 1. So the distractor, it's hard for the distractor. The distractor does not disrupt the synchronization with the primary, and the communication with the primary is still established. However, as we move to frequencies close to the right-hand side of the Arnold tongue, okay, what we see is that now the synchronization with the primary drops down to 0.4 or even lower values. So it means that the distractor has disrupted the communication that was established between the primary and the receiver. So we observe that inputs with higher frequency than the natural frequency of the network are more robust to distractors. Again, this is again due to the role of inhibition, because for frequencies close to the left boundary of the Arnold tongue, the inhibition is active when the distractor volleys arrive. So then the distractor is ignored and communication is established with the primary. However, for frequencies closer to the right boundary of the Arnold tongue, when the distractor volleys arrive, in many cases, inhibition is less present, so they can produce an effect on the target network and destroy the synchronization properties with the primary. Okay, so this is one of the conclusions that we could observe, or the contributions that we could do using math to this question of communication through coherence, is that how we can manage to use, so how using tools from phase dynamics to explain why certain inputs might communicate more effectively than others using oscillatory behavior. But one of the assumptions that I took when I tackled this problem was that the inputs were not very strong, that they were weak in some sense. Because with this assumption, I was able to do the phase reduction. However, what happens is that when we increase the amplitude of the external input for small values of the amplitude, there is a good agreement between the phase reduction and the actual model. So for instance, these are the phase locking regions computed using the phase reduction or using the full system. What happens is that when we start to increase the strength of this input, then the phase reduction is not valid anymore, and we start to there is some disagreement between these curves. So what can we do in this case? Well, since we cannot assume anymore that the trajectory remains close to the original limit cycle, because the perturbation moves the trajectories very far away from the limit cycle, maybe we need to extend the description, the phase description to a neighborhood of the limit cycle, or like to a larger domain. Then, taking advantage of the fact that the phase can also be described in a neighborhood of the limit cycle using the isochrones, we can also compute what is the phase shift if the input arrives not when we are on the limit cycle, which corresponds to the green curve here, but also when we are on a neighborhood of the limit cycle. Because if I apply a perturbation when the trajectory is at this point here, a perturbation, for instance, here in the x direction, moves the trajectory to another isochron, and I can compute the phase difference between these two isochrons, and I can compute the phase response not only for points on the oscillator, but also in a neighborhood. I can do this, and but if I do that, I need control of the amplitude variables, that is how far I am from the limit cycle. So I need an extra variable that measures the distance to the limit cycle in some sense. So to do that, we use the parameterization method, which was introduced by Professor De La Llave and colleagues, that describes defines a parameterization, or like a change of variables in terms of the phase variable theta and an amplitude variable sigma, which measures the distance to the limit cycle, in such a way that the dynamics in these variables is as simple as possible. In this case, it's a rigid rotation for the phase and a contraction for the amplitude, okay? So finding this parameterization K is not easy, but one can develop numerical methods to compute it as the solution of a functional equation that I included here. So for instance, this is a computation for it's a different example, but it consists of also is a model of an excitatory and an inhibitory network that has a limit cycle shown in black, and for which this is in a 3D space. So for which we can compute, for instance, these are like these surfaces are like two isochrons of the limit cycle. And then we can compute in colors here. What we show is that if we apply a perturbation for a point on this isochron, not necessarily on the limit cycle, what is the phase shift? And this is the colors describe the phase shift. We can do the same and computing, like if I put a perturbation on a point on this isochron, what's going to happen to the amplitude? And I can measure the amplitude shift, and this is given by this color. And in this case, it's a 3D space, so I have the amplitude variables are two-dimensional, so I can measure the changes in one and the other. And this is just restricted. This is the plot restricted to the limit cycle. With this, then we can extend the phase reduction to a phase amplitude reduction. That is, if I have my system that has a hyperbolic oscillator and I put a periodic perturbation, P of t, the classical version, which uses only the phase equation and provides the evolution of the phase in terms of this phase gradient, which was the phase response curve that I introduced, the infinitesimal phase response curve that I introduced at the beginning. But if I want to consider just the amplitude variables as well, then I can consider the extended version. And in which case, the phase, the evolution of the phase depends also on how far I am from the oscillator, which is given by this amplitude variable sigma. And then I need to include an equation for the sigma variables. And I can do the same exercise, and if I put a periodic perturbation, I can compute the stroboscopic map. But in this case, I need to control the value of the phase at multiples of the time t, which is the period of the forcing, and the amplitude sigma. And this is to show an example to show that if one uses input with large amplitude, if you restrict to the phase description, you might lose information. That is, for instance, on the left-hand side, we have a situation in which the phase reduction predicts the existence of a fixed point for the stroboscopic map, and the phase amplitude reduction as well predicts the existence of a fixed point for the stroboscopic map. However, the phase is different, okay, at which the fixed point occurs. But as for the example in the middle, and also on the right-hand side, what we see is that the phase reduction, for instance, in the plot in the middle, predicts the existence of a two-periodic orbit of the stroboscopic map. However, considering the phase amplitude description, this doesn't give us a periodic solution of the stroboscopic map, but an invariant curve of the stroboscopic map. So this is to show that the predictions using the phase reduction might lead to wrong conclusions. But considering the amplitude, we can fix this and we can still just get a good approximation of the dynamics. Finally, just let me mention that, for instance, in an excitatory inhibitory network, in this case is described with a different system of equations, but the idea that I would like to give you works as well, is that we have an excitatory and inhibitory network of cells, and then that has an oscillatory solution, has a limit cycle. And now we perturb it with a periodic input. In this case, is a sinusoidal input, or like described by this cosine. And then we let the amplitude of this periodic input to be large. Okay, we don't assume that this must be small. So in this case, these are the Arnold tongues that we observe. So in yellow, we have the one-to-one phase locking region. So the Arnold tongue corresponding to this one. And in pink, as we see, is that when this amplitude increases, these two Arnold tongues, they collide, and here there is some bistability regions, and like a new dynamics emerges that is not observed, just assuming the phase reduction. Okay, so to conclude, I'd like to summarize that I presented a simple model that implements selective communication and communication through coherence via oscillations. And in order to illustrate how reduced by biophysically based model can help to elucidate the mechanisms underlying the dynamics of neural systems. And finally, I showed you that the phase reduction must be assumed cautiously, because if the amplitudes are larger, then we need another set of techniques to tackle this problem. And finally, the goal that was to illustrate that how there are valuable tools in dynamical systems theory that can be of very that can provide a lot of insight into neuroscience problem. Let me finish acknowledging the collaborators, in particular Alberto Perez and David Reine, who were the students that did most of the computations, and also Teresa Seara, Tony Guillamón, and Rafa de la Llave, and the funding agencies. Thank you very much.
Thank you, Gemma. Thank you very much. It was a very nice talk. Let us all thank. Before I open for questions, we have this nice tradition of drawing some gifts during the talks in this conference. So after the questions, we will draw some gifts. So, but let's wait first. And so, are there any questions or comments for Gemma? Please, you can either write or open your microphone. We also have a few attending people at the YouTube, so I don't know if there are questions on YouTube also. So just some on YouTube, some thanking Professor Huguet for the fascinating presentation. So thank you.
Great, Gemma.
Yes. So I guess in the first talk, everyone is still a bit ashamed. So
yeah.
So let's just thank Gemma again.
Need some warm up.
Yeah, thank you.
Thank you.
Thank you. It's this is a very nice subject, and then from me that I am from dynamical systems, to see this application is really exciting.
Yes.
So yes. So thank you very much.
Thanks.
So I pass now for the drawing.
Okay.
If you allow me,
I need to stop sharing, right?
Yeah. You're sharing. Yes. I did for you. So I'm gonna share first. First we'll have. I think you see. I don't know if you see the book. Yeah, I don't see, but if you see, it's fine.
Yes.
Okay. So
it is an offer of mathematical applied mathematical applied computational mathematical society of Brazil.
Yes.
And
SBMAC.
Yes.
Yes. So thanks for the SBMAC for this offer. And then I guess it's Julia or Gabriel, our helpers.
It's me.
Gabriel. So please, Gabriel had put all the names of people that are here on Zoom. Sorry, people on YouTube, we will not add because later on we have to send it by mail. So it's only people that are registered are in the drawing. But Gabriel, if you can share your screen. And,
can I share now?
Yes. Yeah. So Gabriel and Julia, they put all the names in a list. Everyone is here is in the list. Except for us.
My screen.
Yes, we see you.
Okay, so we have here the list of participants and the random.org.
Yeah. Okay, so let's see. Jenna, 7. It's my favorite number.
Yes, and it is the one that we have most.
Marisa.
So 7 is Marisa.
Marisa.
Okay.
Marisa, você ganhou da outra vez também, né?
I was going to say this. I think she's very lucky.
Yes.
She also gets something.
Yes, I have it here.
Okay. Well, I hope you don't get it again because now we are going to draw it. So we'll do the book we did already. So the next gift, it's a kit of our let me just, sorry, it disappeared here from, okay. So that's it. It's a set. It's our bag, our eco bag, celebrating women in mathematics, and the notebook together. So that's the next gift. Gabriel, are you again or Julia?
Me.
Okay, so please. Marisa is out.
Yes, yes.
She got too many gifts, sorry.
Number 12. Alexander.
We can't see it.
We can't, yeah, you didn't share.
Foi mal.
Had to have more.
12.
Yes, okay.
12, okay. So
12.
who's 12?
Alexander Cantoral.
Alexander is our student at the Federal University. Congratulations, Alexander. Great.
Congrats.
So for you, it's gonna be easy to deliver.
Yes.
Okay. So that was it for our first morning session. I would like to thanks again, Gemma. Thank you.
Gemma.
It was very nice. So please, if people can open the microphone for the applause.
Thank you.
Or put your reaction.
Yes. Thank you.
Clap, é ótimo. Obrigada, Juliana. Obrigada, Lamartine. Obrigada, Stefano.
Yes. So thank you very much. Just remind that next we have in 10 minutes, we have 2 different sessions. It's gonna be the applied math and analysis and PDE.
Yes.
And we have 2 different Zoom links, and also we'll be on YouTube live. So we have now a bit of time for a bit of water, coffee, and quick going to the bathroom, and we are back in 10 minutes. So see you all.